So here's part 3 of signal processing practice final exam. So number 6, here given the sequence for this x of n equals the following. We want to find the z transform. So this is a z transform in stability region. So for part A, finding the z transform, that x of n equals 0.8 to the n u of n minus 1.2 to the n u of the negative n minus 1. So our first term, 0.8 to the n u of n, that transforms to 1 over 1 minus 0.8 to z to the negative 1. So our ROC here, absolute value of z is greater than 0.8. Second term, negative quantity 1.2 to the n u to the negative n minus 1. So for a to the n u of negative n minus 1, the z transform is negative 1 over 1 minus az to the negative 1. ROC, absolute value of z is less than absolute value of a. So negative 1.2 to the n u of negative n minus 1 transformed, that's to positive 1 over 1 minus 1.2 z to the negative 1. So our ROC, absolute value of z is less than 1.2, so x of z equals 1 over 1 minus 8/10 z to the negative 1 plus 1 over 1 minus 1.2 z to the negative 1. For part B, determine the ROC. So the ROC here, intersection, occurs z, absolute value of z is greater than 8/10 and absolute value of z is less than 1.2. So as an inequality, 0.8 less than absolute value of z less than 1.2, compound inequality. Okay, so let's see for that inequality, letter C now. Determine if the Fourier transform exists. Let's see if this holds. Just change this, sorry. Okay, so part C, determine if the Fourier transform exists. Does the Fourier transform exist? So the DTFT exists if the unit circle lies in the ROC. The unit circle is, absolute value of z is 1. Since 0.8 is less than 1 is less than 1.2, the DTFT exists. So that's a yes. Part D, determine whether the sequence is stable. So for stability here, a sequence is absolutely summable if the unit circle lies in the ROC. Because the unit circle is inside the ROC, we could say the sequence is stable, absolutely summable, so that's a yes. And for part E, describe the pole zero plot. So pole zero plot description. The poles are at z equals 0.8 and z equals 1.2. Our ROC annulus is from 0.8 is less than absolute value of z, less than the absolute value of z is less than 1.2. So our poles are at 0.8 and 1.2, ROC between them, and we have a 0 at z equals 1. So that's number 6. Moving along to number 7. Describe a digital low-pass filter. Here are the requirements for the pass band, stop band, maximum ripple, and stop band attenuation. For part A, choose FIR or IIR and then justify. So description of a filter problem. So for part A, both are possible. We choose FIR if linear phase is desired. We choose IIR if lower order is desired. Choose FIR using a Kaiser window for controlled ripple and linear phase. Part B, describe the filter mathematically. So describe mathematically the pass band edge, omega sub p equals 0.2 pi. Stop band edge, omega sub s is 0.35 pi. Transition with change in omega is omega sub s minus omega sub p, that's 0.15 pi. So choose an ideal cutoff midpoint. So omega sub c is omega sub p plus omega sub s over 2. Omega sub c is 0.2 pi plus 0.35 pi over 2. So that gives us 0.275 pi. So our ideal low-pass impulse response here, h sub d of n equals this piecewise. And here, where m equals n over 2 for a type 1 linear phase FIR filter. For part C, determine the order estimate. I'm sorry, we're still on part B. Sorry about that. We have to finish up part B. My mistake. Just an addendum to part B here. A window at FIR, this h of n equals h sub d of n, w of n, where w of n is the Kaiser window. So h of n equals h sub d of n omega of n. And I know some people pronounce that differently. I'm just going through this quickly. You have this as a reference. So letter C, what they want us to do is determine the order estimate. So the order estimate for the Kaiser window, n is approximately a minus 8 over 2.285 change in omega. So here a is 40, change in omega is 0.15 pi. So n is approximately 40 minus 8 over 2.285 times quantity 0.15 pi. So n is about 32 over 1.077. N is about 29.7. So n is about 30. So the filter order about 30 depending on your convention. So we'll say 30. Letter D, describe the magnitude response. So the magnitude response, the desired response is the magnitude h of e to the j omega. That's about 1, where our interval here 0 is less than or equal to omega is less than or equal to 0.2 pi. So the transition band here, 0.2 pi is less than omega is less than 0.35 pi. Stop band here, magnitude of h of e to the j omega, that's less than or equal to 10 to the negative 40 over 20, which is 0.01. For 0.35 pi is less than or equal to omega is less than or equal to pi. So our magnitude of h of e to the j omega is less than or equal to 0.01 in the stop band. For part E, describe the trade-offs. So the trade-offs here, increasing order gives a sharper transition and better attenuation, but increases computation and delay. So our FIR advantage, linear phase and guaranteed stability. For the IIR advantage, lower order for comparable magnitude specifications. Okay. Now moving along to number 8. Okay, for number 8, a message signal given here for M of t. And the carrier is C of t. Describe the DSB SC modulation. Part A, find the modulated signal. So modulation and frequency translation. So the carrier frequency here, that 2 pi f sub c equals 2000 pi. F sub c is 1000 hertz. Message frequencies, they're going to come out to 50 hertz and 150 hertz. Our DSB SC signal is S of t equals M of t C of t. So S of t equals this cosine 100 pi t plus 0.5 cosine 300 pi t cosine 2000 pi t. Using cosine A, cosine B, we get 1/2 bracket cosine A plus B plus cosine A minus B, close bracket. First term equals the following: cosine 100 pi t, cosine of 2000 pi t is 1/2 bracket cosine of 2100 pi t plus cosine 1900 pi t. Second term is 0.5 cosine of 300 pi t, cosine 2000 pi t equals 0.25 bracket cosine of 2300 pi t plus cosine of 1700 pi t. So our S of t is going to equal the following: 1 half cosine 2100 pi t plus 1 half cosine 1900 pi t plus 1/4 cosine 2300 pi t plus 1/4 cosine 1700 pi t for the modulated signal. Part B, determine the frequency spectrum. So the spectrum, here are our frequencies: 1050, 950, 1150, 850, putting them in order. Spectral components: 850, 950, 1050, 1150. Part C, find the bandwidth. Bandwidth, highest message frequency is 150 hertz. So our DSB SC bandwidth, B equals twice 150, so that's 300 hertz. So B is 300 hertz. For part D, recover the signal using coherent detection. So here, whoops, sorry about that. Part D, coherent detection, multiply the received signal by 2 cosine 2000 pi t. So 2s of t cosine of 2000 pi t, that equals 2m of t cosine squared 2000 pi t. Using 2 cosine squared theta equals 1 plus cosine 2 theta. We get 2s of t cosine of 2000 pi t equals m of t times the quantity bracket in brackets 1 plus cosine 4000 pi 1 plus cosine of 4000 pi t. So our low pass filter removes the high frequency term. Thus we're going to get m of t equals cosine of 100 pi t plus 0.5 cosine of 300 pi t. And for letter E, explain the carrier phase synchronization error. So for letter E, the phase synchronization error, if the local oscillator is 2 cosine of 2000 pi t plus phi, then after the low pass filtering, we get m hat of t equals m of t cosine phi. If phi equals 90 degrees, then cosine phi equals 0, and the recovered signal vanishes. Okay, so that's part 3. Thank you very much and have a great day.